The Dhauli-Ganga River, flowing through Chamoli district in Uttarakhand, is a steep Himalayan river that joins the Alaknanda River downstream. Originating from glaciated regions, it carries heavy sediment loads due to steep slopes, intense rainfall, and fragile geology. These processes with active tectonics and intense erosion make the Himalayas one of the most dynamic regions on the Earth. Climate change has accelerated glacier melt and altered rainfall patterns. Hence, hydropower development is even more challenging in the Himalayas. Among the major projects here is the Tapovan Vishnugad Hydroelectric Project, a 520 megawatt run-of-the-river scheme on the Dhauli-Ganga River. It plays a key role in harnessing Himalayan hydropower potential and supporting India's renewable energy grid. The 2021 Chamoli disaster. On 7 February 2021, a massive rock ice avalanche from Ronti Peak triggered a devastating debris flow in the Dhauli-Ganga Valley. Around 27 million cubic meters of rock and ice surged downstream, completely washing away the Rishi Ganga project and severely damaging the Tapovan Vishnugad project under construction. Very large boulders were transported and valley walls were scarred. Post-flood studies revealed major geomorphological changes caused by sediment deposition and channel bed adjustment. The event was not a glacial lake outburst but a rock ice avalanche. The event emphasized that Himalayan project planning must consider all hazards, including avalanches, debris flows, and gloughs, especially under changing climatic conditions. Photographs showed extreme damage at the barrage, where radial gates were displaced and flattened. Upstream bed levels rose by about 13 meters. While the project's structure remained stable, restoring its hydraulic performance became the key challenge. For this, NTPC referred the studies to Central Water and Power Research Station, Pune. Hydraulic Model Studies. Considering the urgency of studies with the approaching monsoon, CWPRS carried out mathematical modeling using HAPT mathematical software to check if the annual flood could pass through the silted-up river. High-resolution point cloud survey data supplied by NTPC was used in the studies. Results showed that after local dredging near the right-to-base, the annual flood could safely pass below the high flood level. Further simulations confirmed that the design discharge couldn't pass unless dredging was done. Various trials for dredging were taken, and it was observed that about 0.34 million cubic meters of sediment removal was needed to restore flow capacity. Simulations with this updated terrain indicated that design discharge could be passed safely. The updated digital terrain was prepared from the dredged geometry, which was used to compute new area elevation capacity curves and predict future sediment deposition. A numerical model covering 18 kilometers downstream was also prepared, simulating discharges ranging from 100 to 4,639 cumecs for generation of stage discharge curve at tail race tunnel and inundation profiles for project authorities. Physical model studies. One-dimensional model can't reproduce the complex flow in steep terrain, hence, CWPRS built a three-dimensional physical model at 1:60 geometrically similar scale using the dredged topography. It covered 1.7 km upstream and 0.5 km downstream, including the barrage, stilling basin, and open desilting basin. Simulations confirmed that the design discharge can safely pass under all gate conditions, all open, one closed, or even 65% discharge with two gates closed. Thus, the spillway capacity was found to be adequate under all worst conditions or extreme conditions. Sedimentation and flushing studies. Being a run-of-river project, Tapovan Vishnugad has limited storage but high sediment inflow. Numerical studies were carried out to analyze how quickly the reservoir fills under various discharges. It was observed that for discharge of 300 cubic, sediment reaches up to intake invert in 15 days. To restore capacity and safeguard turbines, drawdown flushing was proposed. Since sediment transport is a complex three-dimensional process, flushing studies were performed on a three-dimensional physical model. Sediment scaling was done by using Shields and Yang's incipient motion criteria, and based on this it was found that silt of 0.23 mm diameter is required to reproduce equivalent D50 of prototype. The deposited bed profile from the mathematical model was reproduced, and bed levels were measured on the showed grid after flushing. During initial simulations, when all gates were open, sediment deposited near the intake and gates 3 and 4 were observed, which was a critical issue that could damage plant's components. Therefore, different combinations of gate operations were tested on the model as shown in the table to optimize flushing efficiency. The best result, where nearly 99% silt removal occurred, was obtained for option 4 as shown in figure, when all gates were open for the first 6 hours, then gates 1 and 2 for 3 hours, followed by gates 3 and 4 for the next 3 hours. These are the actual model photographs for best option 4. Through the combined use of numerical and physical modeling, CWPRS provided an optimized solution for flood passage, sediment management, and hydraulic restoration. With decades of experience and more than 40 Himalayan project studies, CWPRS remains India's premier institute for hydraulic and sediment management research in complex mountain terrains.